Okay, this question is from topic 3, practice set 5. So we are looking at a closed cylindrical structure with a radius x and a height of h meters and a fixed volumes of 10,000 pi meter cube. So then the curved surface area costs $1 per square meter to paint, and the top of the structure costs $5 per square meter to paint, right? Or the base and the top lah. Okay, so basically the circular area, this portion here, right, it will cost you $5. So the top and the bottom, note that it's more expensive, whereas the curved surface area here is slightly cheaper, which is $1 to paint. So now we want to minimize the total cost of painting the entire structure. So what we want to do is we know that the function here, right, we are actually minimizing the cost, right? So step 1 again of Maxima Minima, we want to have the function, right? The function to differentiate, right? We need the function for differentiation. Basically, in this case, because we are minimizing the cost function for differentiation have to be in terms of one variable. Okay, one variable only. So without further ado, let's try to piece out together what the cost will look like, right? So if we know that first of all, right, so the top and the bottom area, that is a pi of x squared, right? So we know that pi of x squared, that is because it's just the area of a circle, right? So there are two of them, one at the top and the bottom. So there is I'm going to multiply by 2, all right, and this area here cost me $5, right, per square meter. So this is the cost for painting the top and the bottom, right? So what about the C for cost? The curved surface area, the part in red. This part, as we know, basically is like a rectangle, right? So it's the circumference of the circle, right, the base, and we multiply it by the height. So it's actually 2 pi x multiplied by height, and this costs us $1 per square meter. So this is the cost here for painting the curved surface area, right? We're basically taking the area multiplied by the cost per area. So from here, this is 10 pi, so 5 times 2, that gives me 10 pi x squared plus 2 pi xh. And we do notice that this part here, there is only there are two variables. One is x and one is h. So it makes sense that it's easier to remove the h since there's only one of it. So if we remove the h, then we basically need to express the h in terms of x. Okay, so this is the part where we need to re-express h in terms of x. Alright, so how do we do that? Then we look at the fixed volume, which is 10,000 pi. So this portion can allow us to form an equation between x and h. Now the volume here for a cylinder, this would be pi base area x squared multiplied by height, which is 10,000 pi, right? So if we were to just remove, cancel out pi on both sides, you can see that we have h equals to 10,000 over x squared. Okay, so this equation expressing h in terms of x allows us to substitute it into this equation here, the cost, right? Because we are minimizing the cost and we have to have the cost in terms of one variable. And you can see that here I'm just basically planting my h in over x squared, right? Just simplify x squared x, and I'm finally left with 10 pi x squared plus 20,000 pi, okay, 20,000 pi over x. Okay, so this is the function that we'll differentiate. So we are minimizing this. So step number 2, we are minimizing this means ideally, you know that we are doing dc dx. So imagine the graph here. There's a cost, and this cost is at a particular value of x, right? This is the minimum cost, right? It's the lowest cost. So we are trying to find out what is the x value that will give us the minimum cost. And the characteristic of this x value at this point is that dc dx should be equals to 0. Okay, and so let's do that. And we find our dc dx. So dCdx, just differentiating 10 pi x squared. Okay, sorry. That will give us 20 pi x. Differentiating x, let's write it as x to the power of -1. You simply end up with 2000 pi x to the power of -2. Okay, so after which you know that again, what you need to do is you need to equate dCdx to 0. This will allow you to find the stationary value of x. Okay, so if we solve dCdx equals to 0, this will allow us to find the x that gives dCdx equals to 0, right? The stationary value of x cos. Now let's do that. So if we put 20 pi x minus 20,000 pi over x squared equals to 0. I'm just going to shift this over to the right. So relatively, it's not too difficult to solve, right? So don't worry too much. Okay, 20,000 pi over x squared. Cancel pi on both sides. Divide by 20 on both sides. You will have multiply the x cube over. You have x cube eventually equals to 1000, which gives you x equals to 10, right? So this we're saying that this value here probably is 10, but do take the due diligence, right? When we find dCdx equals to 0, do not stop there. If you are showing a maximum or minimum, you need to do the second or first derivative test. So step number 4 is to verify the nature of the stationary point. Okay, so you need to verify the nature of the stationary point. So I mean, it looks pretty easy for me to differentiate a second time. Without further ado, I'm going to differentiate this d2c dx squared. Differentiating 20 pi x, I'll get 20 pi. Differentiating 20,000 pi, sorry, I missed out a 0 here. Okay, this should give you eventually 40,000 pi over x cubed, right? And if you were to substitute x equals to 10 in, eventually you are going to get a value of 60 pi, which is indeed more than 0. Okay, so if your second derivative is more than 0, it will tell you that x equals to 10 provides, okay, a minimum value for the cos. Okay, can. So with that, we are done for this question. So you can see the radius here is x, and we have found that at x equals to 10, right? This gives us the minimum value for the cost of painting the structure. Thank you.